Now, rather than writing all this out, which I'd have to do pretty carefully, there's a lot of bookkeeping in front of the camera, I've simply written out the simplified version of the t prime of t expression. And I'm simply going to observe two things. First, I've multiplied through both numerator and, actually haven't done it, but so let's go ahead and do it, denominator, by this square root. Multiplying the denominator through the square root, I get the square root times the square root here. Remember, this is the square root of 9 plus 16 cosine squared of omega t, so that the square root here just becomes a factor, 9 plus 16 omega squared t. Dividing the negative 32 by 2, I get negative 16, which will then distribute through this, and the denominator otherwise disappears. But of course I have to multiply the denominator of my original fraction by the square root of 9 plus 16 cosine squared of omega t, which is going to make my denominator the 3/2 power of 9 plus 16 cosine squared of omega t. Now, looking just at the numerator, what do we have? Well, our I component is going to have a negative 3 omega cosine of omega t multiplied by what was the square root, but now is simply the quantity 9 plus 16 cosine squared of omega t, and that's going to give us this term here. And it looks like I haven't closed my parentheses. So that this multiplied by this becomes this. And then what's our I component down here? Well, we have 3 sine of omega t times I, and that's going to multiply by now negative 16 omega cosine of omega t sine of omega t. We'll have a sine here and a sine here, giving us a sine squared. 3 times negative 16 is negative 48. Our omega comes along, and we do end up with the cosine of omega t. Simplifying the j components similarly gives us the analogous terms. And this is now our expression for the derivative of the unit tangent vector. Now, I said earlier that this is a relatively straightforward process of differentiation. Sometimes the unit tangent vector can be much, much more complex than this. And let me emphasize again, it's important to know the rules of differentiation and to simply apply them to this situation. So, here's our unit tangent vector. A couple of things that we should check. We have a factor of omega on the cosine of omega t here, a factor of omega here, so that there's a factor of omega on the pure numbers that we get throughout the I component, and similarly here. Meaning, of course, we could factor out the omega from the entire term, or from the entire expression. And that would be easy to do. I'm not going to bother to write that down, but it's important that this expression be dimensionally consistent. Omega is going to have dimensions of angle over time, so that omega t becomes dimensionless, and we can take the cosine of it. The cosines and the sines all give us pure numbers, so that the dimension of t prime of t is just going to be the omega times a pure number set of vectors. And actually that is not dimensionally consistent. This thing should actually be in units of acceleration, but the numbers here actually have units of position over units of time. So the 3 and the 48 and the 5 and the 80 would have appropriate dimensions, which when multiplied by the radian per second dimension of omega would give us, for example, meters per second squared, the dimensions of acceleration. So I can just say the denominator is dimensionless, the numerator is in units of omega multiplied by units of position, because our original r of t vector was understood to be a position vector. So our original numbers in the original equation were units of position. And actually I still have a problem with dimensions here that we might reconcile in a minute. Simply see that we can factor out on omega, and we get a unit tangent vector that's given in terms of a multiple of omega.